What's up guys, and welcome to this video tutorial. We are going over some controller design in Mechatronics, and we're going to start off with the root locus, because the root locus is pretty much very independent of all the other controller designs, and it's very procedural and not so difficult to do if you understand what's happening and understand the procedure. Okay, so let's start off by understanding the format of the root locus. Okay, so in order to use a root locus, we need an equation. Okay, and the equation that we use is from the transfer function. Okay, so the transfer function T of S is usually in the form G of S over 1 plus G of S over H of S. Okay, and for the root locus, we only care about the characteristic equation, or the denominator. So the equation we really care about is the equation 1 plus G of S, H of S. Okay, and what we try and do is we try and get this equation, and we equate it to 0, and we try and get this equation in the following format, where we have 1 plus some constant k, okay, times n of s over d of s. Okay, so this is the final format that we really care about and how we want it to look. So basically k is this constant that we're trying to solve for using the root locus, and n of s is just your numerator, that's all that means, and d of s is just your denominator. Okay, so it can be a number of terms. Okay, then when we actually get into plotting the root locus, we need to know what the graph actually represents. Okay, so we have usually a set of axes, and we're plotting on the real and imaginary axes. Okay, so we have the real axis and we have the imaginary axis. Okay, and basically what we call the numerator, okay, the numerator is obviously made up of a factorized function of some sort that says s plus something, s plus, let's say s plus 2, s plus 3, s plus 4, and when we equate those to 0, we call the stuff at the top, we call them the zeros. Okay, and at the bottom we call these the poles. Okay, and poles, or zeros rather, let's start with zeros. Okay, zeros are represented by circles on the axes, and poles, let's choose a different color, poles are represented by crosses. Okay, so if you see a cross, that means it's a pole. If you see a circle there, or an open circle, then that represents a zero. Okay, so that's the first thing that we need to know, and we know that we're plotting on the real and imaginary axis. Okay, so now we can go into the plotting guides. Okay, so there's a number of guides that we follow to plot these graphs. Okay, so the first guide. So guide 1. Guide 1 basically says that the root locus is symmetrical about the real axis. Okay, so this is quite easy to understand. Let's say we have a set of axes and our root locus looks something like this. Let's say our root locus looks something like that on the this third quadrant. Then that means that in the fourth quadrant it's going to look exactly the same. So we have a symmetric graph. If on the other hand it looks, let's say the top of the root locus looks something like this, and we have it going to infinity, then the bottom of the root locus will look exactly like that, and it will go to negative infinity. Okay, so that's guide 1. So that's a pretty easy guide, nothing much to it. So the second guide says that the number of loci, or the number of paths, is equal to the number of poles. Okay, so if we have 3 poles, then we have 3 loci, we have 3 paths in the root locus. Okay, again, nothing too difficult. Okay, guide number 3 says that the the loci start at the poles. Okay, so the loci always start at the poles and terminate. Okay, and they terminate at the zeros or at infinity. Okay, so let's just understand exactly what's happening. Okay, so let's say we have a set of axes like this, and we start off with a pole, and then a 0, and then let's say another pole. Okay, so basically what our loci is going to look like, it has to start at the pole and it ends at the 0, right? And that's the direction. It always goes from the poles to the zeros. However, if there's no 0, so this pole right here has no 0 attached to it, so it needs to end somewhere at infinity. So it goes on forever, basically. If we had another pole on the other hand, let's say we had another 0 there, this loci would look like that, and it would terminate there. Okay, so that's another important thing to note, and that's our guide number 3. Okay, moving on to guide number 4. Okay, so the root locus can only exist on or to the left of an odd number of real poles. Okay, or zeros. Poles, a real number of poles or zeros. And furthermore, it must exist there. So it will always, so they can only live on the left-hand side of an odd number of poles, and they must exist there. So that's basically what I actually showed you, but we'll go through it anyway. So let's say we have that situation, and let's say we have, let's draw in some poles. So if we draw an even number of poles, well, let's have it like this. Okay, so we've got 1, 0, and 2 poles. So that's exactly what we had last time. So we know that it must exist there from the pole to the 0, and then it must exist on the left-hand side of an odd number of poles. So if we introduced another one, let's say we introduced another another pole and another pole. There we've got 1, 2, 3, 4, 5 again. So in between here, there's a connection, and along there, it must exist on the left-hand side. So it has to exist there. But if we were missing this, now we have an even number of zeros and poles. Therefore, we don't have to have it existing on the left-hand side. So this would be what the plot looks like. And these would often go like that and go to infinity. It would usually look something like that, okay? But we'll get to that a bit later. Okay, guide number 5. Okay, so guide number 5 has to do with break in and break out points. Okay, so break in or break away and break in points are found by solving the equation dk over ds is equal to 0. Okay, so break in and break away points, so those were basically what I showed you before, if we have two poles and no zeros, there's a breakaway or break-in point somewhere where basically they shoot away from the axes and go to infinity. Okay, they don't always have to be perpendicular. They can break in from, so we can have something strange. Let's say this was a 0. Okay, we could have something that looks like, let's just erase that. So we could have a situation like this as well, which would be, or rather like that, where it breaks in. The other one would have been a breakaway because it breaks away from the axis. These ones are breaking into the axis. So yeah, that's also a possible situation. So it doesn't have to happen at 90 degrees. It can happen at different angles, and that is another guide that we will be getting into, which is actually the next guide. So guide number 6 says that the loci that do not terminate at 0 approach infinity along an axis. Sorry, along an asymptote. Okay, and the angle can be found using the following equation. So the angle theta is equal to n times 180 degrees divided by z minus p. So z minus p is the number of zeros minus the number of poles. Okay, and those are the ones that actually exist on the real axis. Okay, and n, let's say with n equal to plus or minus 1, plus or minus 3, plus or minus 5. So basically, depending on the number of poles or zeros, we'll pick plus 1 first, minus 1, plus 3, minus 3, and eventually we'll get repeating terms, and that's when we know that we can stop. Okay, so that's guide number 6. There's another equation that we can use as well, which is theta. You can use either of those, is equal to 2k plus 1 over p minus z times 180 degrees. Okay, where k is equal to 0, 1, 2, dot 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 p minus z minus 1. So let's say we had 3 poles. Let's say p equals 3, z equals 1. Therefore, k would go to p minus z is 2 minus 1 would be 1. So what we'd have is it would go from 0 to 1. So we would have k equals 0 and k equals 1. So that's probably an easier method, but both of them do work. Okay, now the question is, for guide number 7, the question that we want to answer is, where's the centroid of the asymptote? So the centroid of the asymptote can be found using theta is equal to the sum of the poles minus the sum of the zeros over the poles minus the zeros. Okay, so let's just actually put an S here. So what we're talking about is we're talking about the algebraic value of the poles and the zeros. Okay, so if we had, let's say on the top we had s plus 2, s plus 3, and at the bottom we had s plus 1, or something like that. The sum of the poles, so there would be 1, 0, so z would equal 1, p would equal 2, and then here we would say s for the top is equal to minus 2 or minus 3, and s is equal to minus 1 at the bottom. Okay, so the sum of the poles would be equal to minus 1, and the sum of the zeros would be minus 5. So we'd have minus 1 minus minus 5, which is 4 over 2 minus 1, which is 1. So the centroid would be at 0.4. Okay, so that's just an example. When we do examples, you'll see how we actually get this. So for that example, we found that the centroid was at 4. Okay, it will usually actually be on the negative axis. So 1, 2, 3, 4. So our asymptote would, for the centroid of our asymptote, would be on that 0.4. Okay, but like I said, when we get into some examples, it should make a bit more sense. Okay, guide number 8, which, okay, so guide 8, we can say the points at which the root loci, or root locus, or the root locus, cross the imaginary axis can be found by substituting S equals I omega into the equation of the intercept. Okay. So it can also be found using the Routh-Howitz criteria, but this is the method that I'll be using, and this is best demonstrated through examples. So when we do the next example, we will go through that. Okay, and that's basically all the rules that we will be needing. So in the next video, so in the next video, we will be using all of these rules and guides to try and draw a root locus plot. And I'm hoping to get through 3 different scenarios so we can just go and explore this concept nicely. Okay, thanks for watching, guys. I hope you found this useful, and tune into the next video.